Lecture 2.9, Adiabatic Processes. A thermal process where no heat transfer, that is, Q is equal to 0, occurs, is called an adiabatic process. To achieve such a process, it has to, 1, occur very quickly, so there is no time or heat to transfer in or out. And it turns out that this is the most common way. So when somebody talks about an adiabatic process, this is what they mean in general. 2, you can have an insulated system where no heat transfer occurs. And of course, it doesn't go in or out. So if I look at the first law, what we're seeing here is that if I have internal energy and I have no heating and I only have work, then this work here is called adiabatic and that's the only way to change the internal energy. So in this case, we're talking about 2 situations. If the work is positive, then what happens here is that I have a volume decrease. But a volume decrease means that I have a compression. Well, then that just means that the work of the piston head is then going to, as it collides with the gas particles, it's going to cause a larger change in the microkinetic energy. So this is not new. This is something that we've have talked about numerous times in this course. So in this case, we see here is that the change in internal energy has to be positive. Yes, they're going to speed up. On the other hand, the work is negative if the volume increases. And if it increases, then we have an expansion. Again, from our argument of work here, so what makes the piston head expands is that the gas collides and loses kinetic energy. So in this case, yes, the internal energy of the gas particles must decrease. That's exactly what we mean by that. And this is what we've been talking about for quite some time. Now, what I want to do here is there's a nice animation here. And I'm going to use, this is, if you go to the adiabatics, link 1, you'll see that there's a video called by Physics Animations. And I think it's a nice one. So let's go look at that. So I'm going to go do a new share. Wait, where am I at? Here it is. So if you look at this thing here, let's just play this for a little bit. So you can see here right now that the blue indicates that the particles are moving slow. But as the compression, you can see that the particles are moving faster. And that's because there's work being done by the piston head. Now we go from faster particles to slower particles because the gas particles are actually doing the collisions here. So what I want to do here is I want to share my screen to make sure that that let's look at this. So what do we have here? We have adiabatic compression. And so if I have adiabatic compression, that immediately says that I have heating since K micro increases. So if you look at this thing, if I take I put some images together just to be faster here, and here's one of the images. You could see here is that in this situation here, I had, let's say I had slow moving gas particles. And then I ended up with fast moving gas particles. And that's because of the work of the compression. So here, what you're seeing here is that this work is positive. So therefore, K micro had to increase. Now, on the other hand, I have adiabatic expansion. And the expansion is caused by the collisions with the gas particles. So therefore, this causes cooling. And the reasons why it's cooling is that now K micro is less than 0. So if I go get that image, and I put it in here, looks like I'm gonna have to move this over here. What you're seeing here is that in this case here, we're seeing an expansion going like this. So this expands, whereas in this case here, we had a compression. And so again, we go from fast particles to slow moving. And again, it's the gas collisions that actually cause this. So then when I look at this thing here, I'm seeing here is that in this case, the work is negative, and therefore the change of the gas, the change in the microkinetic energy has to be negative. Now, there's lots of examples of adiabatic processes. So let's look at some here. So here's some examples. And some demos that we'll look at least obviously they're online demos. So if I look at this, what we're going to see here is that we have the following situation. If I look at what is called adiabatic heating, that clearly means that I have a piston that is compressing. So the work of the piston head has to speed up the gas molecules. So what we saw here in the previous one, we said that so if I look at, if I have a compression, especially if we think about the animation, so we know that a rapid compression increases both pressure and temperature. Now, what happens here is that the inside of the piston can reach temperatures of 400 degrees Fahrenheit, which is about 260 degrees C. So in other words, this is extremely high for compressing things. And the way you do that here is that you have something called a fire piston. And this is a very, very, very cool demonstration. And what you find here with the fire piston, it actually, it's a device of ancient Southern Asia. Used to kindle a fire. You should actually look at this. If you look at the links, so there's a link here called adiabatic. It's under the adiabatic, I believe it's link 5. You should go look at that. Somebody does that in the woods and does and shows you how you can produce a fire outdoors. So picture-wise, it looks something like this. So you have a piston head. Let's see how well I draw this. So I imagine that I have a piston head like this. And what I need to do here is that I need to insulate this thing. So the way I insulate this thing is that I have a plastic or a glass wall to the piston here. And then what happens here is that now I have my plunger or my piston head, and it moves within that container right there. Now what happens here is that now if I look at the piston head comes through, and up here you have the plunger, the handle of the plunger. So I would say here is that this is the handle to compress the gas. And what you do here is that typically what I've done in the past, I've put in, I would have down in here, I would actually put in a tiny bit of tissue and tissue paper. And you can also use cotton. And then what you have in here is that you now have a series of air molecules. So then right in here, you have your air molecules. Now, if you compress this fast enough, here's a high-end image. It looks like this here. You know, I'm going to move this out of the way. Here's an image of the compression, and you could see that it definitely lights up. So let's explain this process here. So what I'm seeing here, so if you quickly compress the piston head, of course, this is adiabatic, so that means then that no heat leaves the system. So what happens here? You have a series of steps here. The air molecules increase internal energy and, of course, temperature. And so what you're finding here is that the tissue cotton is at a lower temperature. As a consequence, you're now going to do what? You're going to transfer from high to low kinetic energy to the tissue cotton. And as a consequence, it increases the temperature and ignites it on fire. So I have a video that I want to show you here, and this is adiabatic link 2. So let's go look at this thing. And this is a professor who has a video on YouTube. So I'm going to get rid of this, and here he is.
This is a demonstration of adiabatic heating. Adiabatic heating is the mechanism whereby diesel engines ignite their fuel. The piston fits inside of a hollow cylinder, and during the compression cycle of the piston, the volume decreases rapidly in the cylinder. When the volume decreases, the pressure increases and the temperature also increases rapidly. So the idea is with what adiabatic means is there's no heat lost or heat exchanged between the interior of the cylinder and the outside world. As long as this happens quickly, then that will hold true. There won't be any heat exchanged. So what I'm going to do is put a little piece of tissue paper in here, and then put the plunger at the top position, screw down this housing, and then attempt to plunge this fast enough to ignite the tissue paper.
There you go. You see how that does that. The one thing that I think he didn't do is that his piece of tissue paper was too big. So if you look at the image, you know, from up here, if you want a big fire, a big spark like this, if you want a big spark like this, you have to have only a tiny piece. His piece was too big, so it didn't really create a huge, you know, spark or fire. Okay, so now let's go to the second one. Now we're going to look at adiabatic cooling. And if I have adiabatic cooling, this means here expansion causes a decrease in K micro. That's why it's called cooling. So what we can say here is that if a gas is allowed to expand quickly, then gas collisions with the piston head decrease internal energy and temperature. So let's look at some examples here. So if I look at some examples, they're not exactly like what we just did here. So here are the common adiabatic coolants. So one of these is when you, so if you spray a can of, let's say, hairspray, or a can of deodorant, it releases the faster moving gas particles first. What's left in the can are the slower ones. So therefore, that implies that you have a decrease in the average K micro, which then tells you that the internal energy, which is proportional to the change in temperature, has decreased. Therefore, one feels the can as being colder. So in this case, it's not that they're colliding with the piston head. They're just being released without any heat transfer. Now, the one that, so this is very, very similar to the one that we just looked at. And what I want to show you here is that here's something that you may have realized. And what you want to do here is that imagine that you have either a bottle of beer or a bottle of soda, and it's been in the refrigerator. And when you look at the neck of the bottle, it's clear. Okay, so that's super important that you look at that. That the air, water vapor in the neck of the bottle is clear. Now, upon opening a bottle, I should say a long neck bottle of beer or soda, you will notice a haze form in the neck. Of course, above the level of the beer or the soda. This haze is condensation due to adiabatic cooling, causing water droplets to form. Now, why is it causing water droplets? Because when you open the bottle, what gets off first is the faster particles, leaving the slower ones, which then the temperature drops. Now, I'm only going to show you one link, but you should really look at both of these. They're pretty impressive. So what I want to play for you right now is I'm going to look at adiabatics, link 3. Highly recommend watching link 4. It's definitely worth it. Okay, so I'm only going to play 3 here. Why? Because it's the clearest. So if I come here, I'm going to get rid of this one. So now, here he is. This is a very, very nice one. So you could see that the way this acts like the long neck bottle is that you have pressurized air. And one of them was pumping the clear soda bottle that had alcohol in it into the bottle. So it's pressurizing it. But as soon as he opens it, you could see that you get condensation, and that's because of adiabatic cooling. Okay, so let's keep going. So now let's get into the mathematics. So the mathematics of adiabatics. Isothermal and adiabatics processes are similar. Because of this, let's compare them. So for starters here, I know that isotherms at the macroscopic level show that the temperature is constant, which then implies that we have our isothermal condition, which says that pressure times volume is a constant. You know, it may have been more useful to just say that delta T is 0, because then it follows very similar to an isotherm. Now I can say the same thing for in adiabatic. So adiabatics at the macroscopic scale occur when Q is equal to 0, but at the microscopic scale require some modifications. So that means here that for Q equal to 0, the requirement is that then that P times the volume times gamma to the gamma power, that this is a constant, where gamma is the ratio of Cp Cv, which is now greater than 1. So this is a requirement. It's not challenging to derive this, but the question is, should we? And I'm saying that it's not necessary. So now let's go look at these things graphically. So graphically, I should say an adiabatic curve is steeper than an isotherm, since V to the gamma is larger than V, since gamma is greater than 1. So now if I plot this, what am I seeing here? So if I plot this here, what I'm going to see here is that I have this. I have, let's say that this is an isotherm. And then here's another isotherm. What you're going to see here is that if this is T1 and this is T2, we know that then T2 has to be greater than T1. So then an adiabatic curve can go from here to there. And this curve here is steeper as it moves, let's say, in this direction. So in this case, I could call this state 1, and I can call this state 2. And so I see here that this guy here is my adiabatic, whereas these two guys are isotherms. So you could see that it does that. So now what we want to do here is that we want to get into the details of what actually happens here. So let me move this up, and then this will be 4 here. Adiabatic processes obey the ideal gas law. The adiabatic gas condition connects two different points along an adiabatic curve with PV gamma equal to a constant, which really means that I have this, that I have P1 V1 gamma and P2 V2 gamma. This relationship is extremely useful. There's another relationship that we'll derive, but this is a very useful relationship. So a second relationship involving temperature and volume can be derived. So if I look at this, I start off with the ideal gas law, because adiabatic processes still obey the ideal gas law, with the exception that we have to include the gamma if I'm going along trying to connect two curves. So then what I'm going to do here is that I'm going to solve for pressure And now what I'm going to do here is that I'm going to substitute. So now I'm going to sub into the adiabatic condition, which then reads that PV gamma, this is going to be nRT over the volume times volume gamma like this. And so this has to equal to a constant. This is still the adiabatic condition here. Now I can rewrite this I could see here is that I can have TV to the gamma minus 1, and then I'm going to have a constant, which is then going to be divided by NR, but then I'm just going to define this as just a different constant, but I'm still going to call it a constant. So then this immediately tells me that I have a second relationship for adiabatics. And in some situations, this is extremely useful. But it's mostly the first one that's the most useful one of all. So now I can now do the adiabatic working. So now here's what we know. All we really care about, what is adiabatic working? So by definition, we know that Q has to equal to 0, where the first law shows that if I have adiabatic work, and of course heat here, that's 0, this is then going to equal the change in internal energy, which is the same as NCV delta T, where we can write this as 3 NR delta T. This is the important relationship right here. So physically, what does this mean here? Well, the adiabatic work is still the area. So if I have a state here and I have one here, if I look at the work here, if this is my adiabatic curve right here, then this guy here has to be what? Has to be the area. This is still the area of that adiabatic curve, where this thing is an adiabatic. But it just turns out to be that it's the value of the internal energy. And this should not be a surprise because this guy right here is what? It's process independent. It doesn't matter whether it's isochoric, isobaric, or adiabatic, the change in internal energy is given by this expression. This is, without any doubt, the most efficient way to calculate W adiabatic. However, there is another way. I think this is less useful, but what you could do here is that if you take this adiabatic work, then this has to be the negative of the integral of V1, V2, where this is pressure like this. And then what you have to do here is that you have to replace pressure with this guy here. So you're going to have to solve for that constant. And if you do this, here's what you end up getting at the end. You'll get an expression that reads 1 over gamma minus 1 times the difference of P2 V2 P1 V1. This is one that works just as well, but I think that the way our system's set up, it's more useful to use the other one. So now we have everything. So in summary, we now have our table. So I've included adiabatic processes, and you could see that we got everything going on here. And again, I dropped minus signs. There should be a minus sign here, minus sign here, minus sign there, and minus sign there.